Z658 lecture 30. So far in this course we have looked at A to D conversion. Apart from studying the basics and how you define various specs and so on, we have seen a simple way of doing A to D conversion, namely the flash analog to digital conversion technique, where the idea is basically that of a dumb search. You divide the input into a bunch of bins and basically figure out in which of these bins the input lies by exploiting parallelism. You put many guys on the job at the same time. So understandably the whole process is quite quick, but as the number of bins becomes larger and larger, you can see that the complexity increases exponentially as the number of bits of resolution desired. And one might conceive of other smarter ways of doing the search, okay, and every one of those techniques will translate into a different A to D converter architecture. However, in a course like this, it's obviously not practical to cover every possible architecture because it's just going to take too much time. The basic idea in this course is to do at least two architectures with with reasonable depth, so that you are able to design something, and also with in this process I hopefully will also learn how to be able to learn yourself when you perhaps read a paper or look at a book or something which discusses another architecture. It all doesn't sound like rocket science to you. It should all be pretty self-explanatory, and you should be able to go through the details and figure it out. So one architecture that we have covered is the flash. Another architecture that I will cover in detail is what are called this family of oversampled data converters, right? In short, known as sigma delta data converters. That technique basically exploits negative feedback. You kind of take a lousy quantizer, put it in a feedback loop, and make it behave well. And a quantizer is something with an analog input and an analog output. You want analog to analog, all right, but you can think of it of doing this in two steps. One is analog to digital, right, and then you need something to convert back to analog. So this is an A to D and a D to A converter in cascade. So we'll spend some time looking at D to A converters and understanding what these things do, so that we can put these two together, the A to D converter, the flash and the DAC together, and make a quantizer. Then you put it in a feedback loop, make a new kind of A to D converter where the equivalent resolution of that converter is much larger than the lousy quantizer that you take and put in the feedback loop. If you don't understand what I'm talking about, never mind. Okay, you'll understand as time goes along. But for the time being, we will get on to digital to analog conversion. The basic idea here is to take a digital word with n bits, for example, the output is an analog quantity. It could be voltage, it could be current, it could be charge, and the analog quantity is within quotes proportional to the digital code that you put in, right? So if it's an n bit word, they must be at the output 2 to the n distinct levels. So in other words, if I plotted on the x-axis, what should be there on the x-axis now? If I want to characterize this D to A converter, what should be there on the x-axis? The digital code. So I will take again a 3-bit example. So the codes will be 0, 1, 2, 3, 4, 5, 6 and 7. When the digital code is 0, perhaps you want no output. When the digital code is 1, you want something like this. You can conceivably, in the ideal situation, draw a straight line through all these points. This is without loss of generality. You can assume, for example, that the output analog quantity is a voltage, in which case the y-axis will be in volts, the x-axis is dimensionless, and this is the step size of the, also called the LSB of the DAC. This is output is an analog quantity, right? So when you say the LSB of the DAC is, whatever, 1 millivolt, what it means is that the change in the analog output for one LSB change in the digital input code is 1 LSB, is, whatever, 1 millivolt. Does it make sense? Okay, so this is what you would like to have in principle. In practice, what can you assume? I mean, these are all made with, you probably have some analog circuits doing all this. So there will be device mismatch and stuff like that. So without getting into the details, you wanted something ideal like this. In practice, you will get something which is where if you make a measurement on a practical DAC, what would you expect? Do you think these black dots will all lie on a straight line? Most likely not. So perhaps something is like this. The analog output values, when joined together, will not be a simple straight line. There will be deviations, and just like how we went about doing this with respect to A to D converters, you can define similar errors. The first error is offset, alright, and the basic mechanism is all quite straightforward. There is nothing rocket sciencey about this. This is the ideal stuff, okay. If all of them are off, deviate from the ideal line by the same value, offset it, okay. That is, the red are the real converter, the black dots are the ideal outputs, and you can see that the red dots are simply offset from the black dots by a fixed quantity. And just like in the A to D converter case, offset is typically benign in most systems and can be corrected by other means. Okay, if this is a part of a system, there is probably some kind of offset correction loop that is there, goes around the whole system. So most cases it's benign. The second kind of error is gain error. Again, this is what the ideal characteristic should have looked like. And this is what the actual characteristic looks like. And in other words, the LSB size is the same, but it is not what you anticipated it to be. Alright. So the change in the analog output for a change in the input code by 1 is not what you would expect, and this corresponds to gain error and is also mostly benign. Okay. The third kind of error is, of course, and things aren't so nice, to make things clearer, I will stretch out this diagram. So the red dots are what you measure, let's say, for a practical converter, and the black dots are what you would expect for an ideal converter. So this is the in other words, the red guys don't straddle and when you join all of them together, they don't lie on a straight line. So one thing that you can do, so just analogous to what you would do in what you did with respect to an A to D converter, you can define, if you knew the LSB size, okay, as I've done in this example, then you can define the differential nonlinearity as a function of code. How do you define differential nonlinearity in an A to D converter? I mean, in an analog to digital converter, you measure the width of the analog input voltage that is required to give, that gives a particular code. That's the width of that code, right? We know that in principle, if the A to D converter is ideal, then the width of the code must be full scale divided by 2 to the power n, alright. In practice, it will not be that full scale by 2 to the power n, there will be deviations depending on a random device mismatch, things like that, okay. You know that the nominal must be so much, so all the real information is in the deviation around the deviation around the nominal, right. So it makes sense to only quantify that, and it's understood that the deviation should be around the ideal LSB. Similarly, in a D to A converter, you know that the change in the analog output voltage should be 1 LSB. When I increase the code, I find that it could be more or less than 1 LSB. It typically is around 1 LSB, but for some codes it could be greater and some codes it could be smaller. So one simple way of this thing is V out of K minus V out of K minus 1 is the change in the analog output voltage, corresponding to the code K, alright. This minus 1 LSB divided by 1 LSB is the differential nonlinearity corresponding to a code K, and this is a dimensionless quantity, since it is normalized to the LSB of the converter. Similarly, the integral nonlinearity INL of the code K is defined as, you can evaluate it as being the, just like in the case of an ADC, you can evaluate it as the running sum of the DNL, but what does it physically mean? So it is defined as how far the actual output is away from the ideal output. So it is basically V naught of K minus, in this example it is K times LSB divided by 1 LSB, right? It's quite straightforward, and again this is dimensionless. And just like how you had in an A to D converter, you can derive a simple relationship between the DNL and INL. The INL is simply the running sum of the DNL. Does it make sense? And in practice, you will never have converters which have only offset error or only gain error. You will have, everything will be combined together. So in general, what you will find when you measure a data converter or D to A converter is something like this. If there are codes on the x-axis, if what we showed was all for simple example. If for example you took a 10-bit D2A converter, the codes will run all the way from 0 to 1023, right? And for each code you will have one analog output, and you perhaps would get, let's say, something like this. I mean, this is not really a curve, it is just one dot for every code, alright. If you have to compute the DNL, INL of this output, how do you, the first thing is to find the DNL and the INL, the first thing is to find the LSB size, right. So, what do you think I should do? I mean, clearly it doesn't make sense to use, I mean, within quotes the, I mean, when you buy a DAC, the manufacturer will say that the nominal LSB size is likely to be so much. But even if there is a small deviation in the LSB size, you can see that, for example, this is what you would expect the curve to be ideally. Let's say the LSB size was slightly off, then you would see what you would actually measure would be something like this. And you can see that even though this lies on a perfectly straight line, you would think if I just use this as the, I mean, from this curve, if I compute the LSB size and this is what I thought my ideal was, I clearly see that even though the converter is perfectly fine, if it would seem as if there is a large INL here. Okay, the INL is going on increasing from 0 to something very large and positive. So that's clearly not the converter's fault, it's just some gain error, and as we said, gain error is benign. So we should be able to take out the same thing with offset also. If the curve was like this, the pink one here, then there's nothing really wrong with the converter, it's just that all this characteristic is completely shifted. So with the offset curve, if I simply directly use the definition of INL with the wrong LSB size, okay, when I compute DNL of this curve, what would I get? On the pink curve, what would I get if I compute the DNL? I would get 0, alright, but what would I get as INL? I will get a constant corresponding to this spacing, correct? On the other hand, what about this chap? If I compute the DNL, what do I get? I will get a constant DNL, and the INL will keep, the INL is 0 here, and which is the deviation, the INL which is the deviation from the real characteristic and the ideal characteristic is 0 here and goes on increasing, and that makes sense because if the DNL is constant, then the INL, which is the running sum of the DNL, must go on increasing. Is that clear? Clearly, even though both these converters are perfectly okay and I mean completely harmless, it would seem, okay, that they have terrible amounts of DNL and INL simply because we have not really taken care of offset and gain errors in the converter. So the first step is to remove offset and gain errors. So the clean thing to do, just as we did for the case of an A to D converter, is fit a straight line. You know the x values, you know the y values, right? So you fit a straight line perhaps like this. Alright, this is clearly not the best fit straight line because I can simply move this up a little bit and I guess get reduced error, but anyway. Alright, so once you get the best fit straight line, what all do you know? You know the LSB size. Once you know the LSB size, finding the DNL and INL will be actually quite straightforward. In the equations, all that you didn't know was the LSB size, and to compute the INL, what is the INL here? For example, at this code, what is the INL? It is simply this chap here. That's the INL. The black is the ideal characteristic, alright, and the red is the actual characteristic. The black is the ideal characteristic corrected for both gain and offset, alright, and the deviation between the ideal and the actual characteristic is the, by definition, the INL. So you can see that the clearly that the line marked in green is the INL of that code. Is that clear? In general, if you see an INL with the same sign throughout, so in general what you would do is, in this case, the INL is plotted as a function of code. INL in LSB, okay. Ideally, what should it be? In an ideal D2A converter, it should be 0. In this particular example, what do you think it will be? First it will be negative, okay, then it will go to 0, then it will go positive, kind of reach a maximum around here, I guess. So if you see an INL which is always positive, what can you conclude? That basically means that offset and gain errors have been corrected for, alright. So there is always a possibility of improving the, it's the same converter, okay, so it's just a matter of specmanship. So you can always do better by removing gain and offset errors. So this is what is called the best fit DNL and INL. Okay. You could also do what is the so called endpoint INL, right. So okay, so here the assumption is that the beginning and the end are correct, and you draw the straight line between the beginning and the end, and the INL, as you can see in this particular characteristic, is clearly always positive, okay. So you can definitely make things better by moving the straight line around a little bit, which is what the best fit does. DNL, INL and all this other stuff are what are called static parameters, or this corresponds to static characterization of the D2A converter, alright. The output of a D2A converter from the spectrum point of view, a D2A converter can be thought of as simply a device which converts stuff from discrete time to continuous time. So you have some samples, okay. So you have some samples x of k with a Fourier transform x of k e to the minus j omega k and as usual we use the small omega for discrete time frequency, and in continuous time, so in other words the discrete time sequence is doing this, alright, and what we are doing is, this is just index, right. So this is 0, 1, 2, 3, etc. So what we are doing is converting this into a continuous time signal, where we replace the discrete time impulse with, in the simplest case, a Dirac delta or a continuous time impulse, and the spectrum corresponding to the impulse train on the right is the Fourier transform is x of j capital omega is nothing but x of k e to the minus j capital omega kt. Correct? This is what the discrete to continuous time conversion is doing. T is simply called the speed of the DAC or the update rate of the DAC. The output of the DAC is changing every t seconds. Now, from these two relations, this and this, what do you see? So, x of j capital omega is nothing but whatever, what am I getting? X of omega by t. In other words, to look at the spectrum, if this was, we only deal with real signals, right? So if this was, say, pi the discrete time spectrum, as you all know, is periodic with a period of 2 pi, okay. To determine the relationship between the continuous time spectrum and the discrete time spectrum, you replace, this keeps extending all the way to infinity. It's common practice to only retain this part, alright, and filter off. Please understand that if this was the discrete time sequence, the continuous time waveform you actually wanted was perhaps something like this. Okay, so what is that? It is a smooth version of that impulse train, correct? And smoothing is nothing but filtering. So the bottom line is you need what is called a smoothing filter at the output of the DAC to get rid of all these aliases, images. So this is the characteristic of the smoothing filter. The larger the bandwidth of the discrete time signal when compared to pi, you see that the smoothing filter must become sharper. This is exactly analogous to what we had with an A to D converter, right? So if the input signal occupied a bandwidth almost close to Nyquist, then you really need a sharp anti-alias filter, otherwise aliasing will kill you. The same thing here, if your filter is not very sharp, then this smoothing process is not as smooth as it looks. There will be rough edges, and which is basically something which is probably undesired. So to make the smoothing filter requirements easy, what they would do would be oversample the signal so that this digital signal occupies a bandwidth much smaller than pi, in which case the smoothing filter, the rate at which it falls off, can be modest. I mean, there are a couple of disadvantages of a DAC like this. What do you think they are? A DAC which puts out continuous time impulses, as you would most likely see in a signal processing textbook, right? In practice, what is the problem with? Of course, it's very difficult to generate the impulse, fine, and more important, I mean, okay, and even if you generated the impulse, it's such a terrible waste of power, because what you want is only this energy here, and now you're generating this big, you're generating images all over the place, and also trying to get rid of it by putting a smoothing filter. So clearly from a power efficiency point of view, this is first of all it's difficult to do, and then it is inefficient, so why bother doing it at all? So instead of generating x of k delta of t minus kt, this is the impulse DAC, it makes sense to think of a Saner pulse shape. Okay, so this is x of k, p of t minus k. Can you comment on the spectrum of this and the spectrum of this? How would I get the spectrum of that from the spectrum? I know the spectrum of this character here. It is x of k delta of t minus kt. Instead of delta of t minus kt, if I put p of t minus kt, what do you think the spectrum of that character there will be? So basically what he means is that you need to take this stream of deltas and pass them through a filter with whose impulse response is p of t, correct? If the spectrum of this guy was this, then the spectrum of this chap will be x of j omega times p of j omega. Alright, so this is equivalent to taking this string of Dirac delta functions, passing this through a filter with an impulse response p of t, and then you get what you look, when you look here, what you will see is something like, let's say I took some arbitrary pulse. Intuitively you must be able to see that when I superpose these guys together, I mean that waveform is a lot smoother than, to begin with, than these spikes which go all the way to infinity, right? So clearly if I use this characteristic for p of t, the spectrum, the images would naturally tend to reduce as the frequency goes up. If with an impulsive DAC, the images are all of the same intensity, right? So once you choose a pulse shape, there is a possibility to knock off, or I mean reduce the intensity of some of those images. Does this make sense? Okay. So some common pulse shapes used. This is what is called the NRZ pulse. The NRZ stands for non-return to 0. So the DAC waveform would look like this. Okay, so this is t, this is 2t, this is 3t. Alright, so this is x of 0, x of 1, x of 2, x of 3. Okay, so clearly this is this is also a rough waveform, but this is certainly smoother than having impulses, because the discontinuity in the case of impulse is infinite, whereas here there is only finite amount of jump. Spectrum of a DAC of this nature, so x of j omega multiplied by the frequency response of this pulse. This is a rectangular pulse, so what is the, so it's nothing but AT sync ft is amplitude, so it's t sync ft, okay, e to the minus j omega t by 2, because the average delay of this pulse is t by 2. Okay, so I'm only so what do you think happens to the spectrum if the original spectrum was, for example, like this? So the black one stands for x of j omega. How does sync ft look like? So what happens to the sync at 0? Okay, so this will be multiplied by something like this. What is it at 1 over t? It is 0. Well, you can see clearly that the resulting spectrum is, there are two things to be noted. One, of course, is that when over the input signal band itself, this is the signal band. What do you see? What is the sync doing? So it's basically low pass filtering even the signal in the band. So this is often called sync X droop. And as you can see, it is also causing some image filtering. The images are not as bad as they were with the basic the impulse tag. Okay. Another commonly used pulse shape rather is, what is this pulse shape? What could you likely call this? This is the so-called return to zero RZ pulse. Stands for return to. What does the Fourier transform of this guy look like now? This will be A T sync FT. A is twice, T is half. So it is still T sync F T by 2. That's the e to the minus j 2 pi F T by 4. Okay, that's the P of F. So if I draw the spectrum on the same picture, what can you say about the droop, sync X droop? Is it be smaller or larger? It will be smaller, okay, and this must be 2 by T, okay. So this is for an RZ DAC. This is for an NRZ DAC. So when you compare the RZ and the NRZ DAC, what can you say? The droop is less, okay, but what about the image filtering? It's certainly less for a return to zero DAC. Okay, does it intuitively make sense looking at the pulse shape? The time duration is smaller, so if the time width is small, the frequency width must be large. So it must be letting in, so its image filtering qualities must definitely be poorer than what you would get for an NRZ DAC. And you can see that also from the obvious question is if clearly NRZ seems to be better, why bother about RZ at all? It turns out there's definitely a place for RZ DACs, and I'll talk about why RZ DACs are important tomorrow.